true stars, like our sun, only much denser. We've seen that in gravity, and then we've seen a bunch of light come off of that.
For the first time, we detected gravitational waves that were coming not from the collision of black holes, but from the collision of two neutron stars.
Neutron stars, born from the cataclysmic demise of massive stars, defy the boundaries of physics with their mind-bending properties. Ever wondered how an object the size of a city could possess a mass greater than our sun? And that's just one of the myriad mind-bending properties they possess. So today, we will shed light on the mysteries surrounding these celestial marvels, offering an in-depth exploration of their formation, properties, and the profound role they play in unraveling the fabric of the cosmos. Neutron star is like the leftover magic of a once giant superstar, now collapsed into a mind-blowingly small package. Forget vast expanses, we're talking a radius of around 10 kilometers, making your favorite pizza place look like a cosmic giant in comparison. These pint-sized powerhouses boast a mass of about 1.4 times that of our sun, crammed into this minuscule space. Neutron stars are basically the David Blaines of the cosmos. Tiny, dense, and absolutely mesmerizing. In fact, next to black holes, they hold the title for the smallest and densest known stellar objects. Think of them as the cosmic bonsai trees, compact but packs a punch. But how do these cosmic miracles come to be? Well, imagine a star, not just any star, but a superstar with a mass of 8 times the sun or more. As it ages, it turns into an iron-rich core through stellar nucleosynthesis. Once it's burned through all its nuclear fuel, the core has to stand on its own, and that's when things get dramatic. The core's mass exceeds the Chandrasekhar limit, electron degeneracy pressure surrenders, and the core collapses. Picture this like a cosmic game of dominoes. One thing leads to another until, bam! Temperatures soar, electrons and protons team up to become neutrons, and voila! A flood of neutrinos is released. The outer envelope of the star gets flung outwards, resulting in a dazzling supernova. And what's left behind? Our neutron star, ladies and gentlemen. Hold on tight because here's where it gets mind-bogglingly cool. As the star collapses into a neutron star, it retains most of its angular momentum. Translation: it starts spinning like your favorite vinyl record on steroids. Neutron stars can go from 1.4 milliseconds to a leisurely 30 seconds per rotation. And we're not done yet. Brace yourselves for the gravitational workout. Picture a place where gravity is so intense it makes the Earth look like a featherweight. We're talking surface gravity that's a whopping 1012 to 1013 times stronger than what we feel on our home planet. It's so powerful that the escape velocity from a neutron star is over half the speed of light. And neutron stars are super dense. Imagine squishing the entire sun's mass into a space as small as a single atom's nucleus. That's how packed they are. Grabbing just a tiny bit of stuff from a neutron star, like a teaspoonful, would weigh more than 900 huge pyramids. And if Earth were as dense as a neutron star, it'd fit inside a space the size of the Arecibo Observatory. These stars cool down crazy fast, going from really hot to shooting out X-rays in just a few years. Their mind-blowing density and tiny size make them super fascinating in the universe. Inside these stars, it's a cosmic mystery. Quantum physics puzzles like superconductivity and superfluidity mimic a labyrinth. Observing these from parsecs away adds to the puzzle. Picture neutron stars as colossal atomic nuclei, sharing traits but blown up to a celestial scale. They're cosmic rock stars with striking similarities to atomic nuclei. Neutron stars and atomic nuclei share forces holding them together, but they're different fruits. Nuclei stick due to the strong interaction, while neutron stars are all gravity. They're not quite the same cosmic breed. Nuclei are dense apples, while neutron stars are layered oranges with varying compositions and densities. Now, let's talk about the extreme conditions near the surface. The neutron star's gravity is like a cosmic vacuum cleaner, accelerating anything falling towards it to mind-bending speeds. And here comes the fun part. Tidal forces near the surface can cause spaghettification. No, not the Italian cuisine kind, but the kind where intense gravity stretches and pulls objects into long, thin strands. The Tolman-Oppenheimer-Volkoff limit typically at 2.1 times the Sun's mass for neutron stars, might now stretch to 2.16 times. PSR J0740 plus 6620 at 2.14 times the Sun's mass is like the Beyoncé of neutron stars. Stars between 1.4 and 2.16 times the Sun's mass could be neutron stars or high-mass white dwarfs, blurring cosmic boundaries. Crossing 2.16 times the Sun's mass can turn a star into a black hole, but between 2.16 and 5 times the Sun's mass, speculation reigns. Quark stars and electro-weak stars could emerge, the enigmatic cosmic rock stars yet to take the stage. Now let's talk about temperatures inside neutron stars. Picture this: a freshly baked neutron star has a toasty interior of around 10 to the power of 11 to 10 to the power of 12 Kelvin. Neutron stars boast magnetic fields from 10,000 to 100 billion Tesla, eclipsing cosmic levels. Imagine a field so intense it can levitate a frog. These fields vary and define neutron stars, shaping spectra and pulsar rhythms. Magnetars steal the spotlight with fields of up to 100 billion Tesla, driving types like SGRs and AXPs. Their chaos includes polarizing vacuum, causing photon dances and creating particle pairs, and bending cosmic rules with energy densities surpassing ordinary matter. But how do neutron stars get such mind-bending magnetic mojo? The origins remain a cosmic conundrum, with one hypothesis suggesting flux freezing. It's like conserving the cosmic magic during the neutron star's formation. As the star collapses, the surface area shrinks. But if the original magnetic flux is conserved, voila! The magnetic field becomes a powerhouse. It's a bit like starting with a giant pancake and ending up with a silver dollar, but the syrupy magnetic field stays thick. Now let's talk gravity. And we're not messing around here. The gravitational field at the surface of a neutron star is a jaw-dropping 2 × 10 to the 11 times stronger than what we feel on good old Earth. This intense gravitational field acts like a stellar lens, bending the radiation emitted by the neutron star in such a way that even the usually invisible rear surface becomes visible. Imagine catching glimpses of the celestial flip side. It's like the ultimate backstage pass to the cosmic show. Now, if you're ever skydiving on a neutron star, hypothetical of course, the gravity is so extreme that an object falling from just 1 meter would hit the ground at a mind-boggling 1,400 kilometers per second. That's faster than a cosmic cannonball. But there's a cosmic catch. Before it even reaches the ground, the tidal force would kick in, causing spaghettification. Yes, you heard that right, spaghettification. It's like turning any object into a cosmic noodle due to the insane gravity. And here's a mind-bender for you. Time on a neutron star is a bit like a space-time warp. 8 years could roll by on the star's surface, but guess what? Back on Earth, a solid 10 years would have done its thing. Thank you, time dilation. Now let's dive into the structure of these cosmic wonders. Current mathematical models tell us that a neutron star's surface is like a solid lattice made up of crushed atomic nuclei, with electrons flowing through the gaps like a cosmic river. Imagine it as the neutron star's own dance floor, but instead of disco lights, it's flooded with extreme gravitational vibes. What's even more fascinating is the potential presence of iron nuclei at the surface, possibly because of their super high binding energy, or the heavy elements, being the rebels they are, might just sink beneath the surface, leaving only the lightweight nuclei like helium and hydrogen to party on the outer layers. And let's not forget the neutron star's atmosphere. It's hypothesized to be thinner than a human hair, controlled entirely by the neutron star's magnetic field. Beneath this ethereal layer lies the cosmic crust, super hard and smooth, like the neutron star's dance floor. Go any deeper and you'll encounter nuclei with neutron armies, stable against the odds due to the insane pressure. The inner crust of a neutron star creates nuclear pasta, akin to layers of lasagna under cosmic pressure. Gravity holds these structures in the star's kitchen, a celestial cooking show with unique recipes. Deeper in the core, a secret sauce emerges, a mystery yet to unravel. One model proposes a superfluid core of nitrogen-degenerate matter, a stellar smoothie with neutrons, protons, and electrons. Other exotic possibilities are on the menu. Imagine strange matter, not your usual cosmic flavor, containing strange quarks hanging out with the regular up and down quarks. It's like a cosmic cocktail with a twist. Or how about the matter with high-energy pions and kaons joining the neutron party? And if you're feeling really adventurous, the ultra-dense quark-degenerate matter might be in the mix, turning the dance floor into a cosmic rave. Now, these are not just random dance moves. They're the cosmic waltz of nuclear matter, with each step revealing a bit more about the inner workings of neutron stars. And that's a wrap! So what do you think about neutron stars? Share your thoughts in the comments below, and don't forget to like and subscribe to our channel for more.